All right, this is Algebra 2. Lesson 6.1, we're starting to use properties of exponents and using them to evaluate and simplify expressions involving powers. We're actually going to stay away from the second goal right here. We're not going to fool with scientific notation in this lesson, beginning on page 323. First thing we got is a definition of what scientific notation is. You still need to know what it is just in case. Scientific notation is good because everything's written based on powers of 10, meaning you multiply everything by 10 and then you raise that to the number you're looking for. What that does is it just allows you, instead of writing a number like 100,000, it just, when you're multiplying something by 10, it allows you to move that decimal over each time you raise it to a power. So you'd move it once, twice, three, four. You'd move it 5 times in this case, and 100,000 would become 1 or 1.0 times 10. And we moved it 5 times, so it'd be to the 5th power. That would just be an example of scientific notation. The key with scientific notation, it has to be between the numbers 1 and 10. And in fact, it has to be smaller than 10, but it can be 1. Okay, here's what we need to look at. It says let A and B be real numbers and let M and N be integers. That means not fractions here. We're not dealing with fractions there just yet. First one is the product of powers property. A to the M, that's how you read that, times A to the N. What you do with exponents, anytime you are multiplying bases, you add exponents. We know how to do that already. We know if we have x, if we're foiling something, times x, if we do the first two terms, we know we have to do x to the 1 plus 1, and that's why we get x squared. So it's the same concept. Anytime you multiply, multiplication goes with addition. You add exponents, m plus n. The same thing's true, or not quite the same thing's true, but when you're raising a power to a power, notice the difference between the first one and this one. Now it's m being raised to the nth power. So a power is being raised to a power instead of adding them in this case. Now is when you multiply the bases. So anytime the bases multiply themselves, you add the exponents. Anytime the exponents are being raised to another exponent, you multiply the exponents, a to the m times n. What that means is a, b, this is the product, this is the power of a product property, a times b to the m power. You have to make sure you distribute that m to both of them. That's like saying a to the m times b to the m. Make sure it's given to every part of the term. And we'll have examples to explain what that means in a minute. Okay, negative exponent property. Anytime something is raised to the negative exponent, a to the m, what you need to do is you need to ride the elevator. Everything's considered to be over 1. Anytime something is raised to a negative exponent, take whatever that something is and ride the elevator down. There can't be 0 at the top of the fraction, otherwise it would be 0 divided by something which would give you 0. So you're left with 1 at the top, and then when a comes down, it becomes raised to positive m. In that case, a can't be 0. So all a negative exponent does is tells you to ride the elevator. Had it been at the bottom, what if it said 1 over a to the negative m? You would do the same thing, except now a to the negative m would go up top, and it would be a to the m over 1. Anytime something's raised to a 0 power, it is equal to 1. Okay, the reason that is, if you have 3 to the 4th power, we know that that means 3 times itself 4 times. We know 3 to the 3rd power means 3 times itself 3 times. We know 3 to the 2nd power is 3 times itself 2 times, and we know 3 to the 1st power is 3 times itself no times. Okay? The reason 3 to the 0 power, the reason anything to the 0 power is 1, is because not only is 3 to the 4th power 3 times 3 times 3 times 3, it's actually times 1. And the reason that you don't ever write it that way is because there's no reason to write something times 1. The same thing's true with the next one. 3 to the 3rd power is not 3 times 3 times 3. It's actually 3 times 3 times 3 times 1. 3 to the 2nd power is not 3 times 3. It's 3 times 3 times 1. And 3 to the first power is not 3, it's 3 times 1, which leaves that 1 still comes down. And that's the reason anything to the 0 power is 1. And in quotient properties says that anytime you have a dividing by a, you subtract the exponents m minus n. When we were multiplying a times a, we added the exponents. So multiplication goes with addition, and division goes with subtraction. And then a over b to the m power means a to the m over b to the m. And this was just like the last bell word problem we did. 1/2 to the 5th power. We made sure both of them got raised to the 5th power. Just like this one here, where a b to the m power, you distribute the m to both of them. This one, you're going to distribute the m to both of them, and it becomes a to the m over b to the m. Okay, here's the first example you had to do. 7 to the 6th over 7 to the 3rd. It's division, so you subtract exponents. 7 to the 6th minus 3, which is 7 to the 3rd, which means 7 times 7 times 7, which gives you 343. The next one, 3 to the negative 2 power. Remember, that doesn't make it a negative number. 3 to the negative 2 is over 1. Everything's over 1. All a negative tells you to do is ride the elevator. So 1's going to be at the top. 3 now is to the second power. It's positive, and we know 3 squared means 3 times 3, and that's why you get 1 over 9. Remember, a negative exponent does not make a negative answer. It just makes a reciprocal. It just makes you flip it, or it just rides the elevator. C says 3 squared squared. You read it just like that, or 3 to the second power to the second power. Now you don't add the exponent since it's a power being raised to a power. You multiply 2 times 2. You get 3 to the 4th power, which when you multiply 3 times itself 4 times, you get 81. Okay, here's 3 example problems. Take about a minute and do those 3. All right, let's take a look at this. I know most of y'all are spending more time simplifying it than anything else. What you need to understand, though, at this point, you need to understand with a, it's 3 to the 4th power being squared. This is one of those instances where you actually want to multiply the exponents. So 3 to the 4 times 2 gives you 3 to the 8th power, not 38. Make sure you're writing small enough where you can see it. 3 to the 8th power. On your calculators, there's a nice, neat little button. You could punch in 3, and you can punch in that caret button to the 8th power. You get 729, save you a little time. B says 5 over 8 to the 3rd power. Remember, both terms get raised to the third power. So 5 to the eighth power over, I'm sorry, to the third power, excuse me. 5 to the third power over 8 to the third power. 5 to the third power is going to be 125. 8 to the third power is going to be 512. Let's just leave it like that for right now. It could possibly simplify, but we're going to spend too long fooling with it. I'm sorry, I did, when I did it, I did 3 to the sixth power like a dummy. 3 to the eighth power, everybody, is 6,561. 65, 61. Then C is negative 2 to the negative third power. Remember, all of this right now is over the number 1. What's being raised to the negative exponent is this. So when it rides the elevator, it goes down. Now it's at the bottom of the fraction. It's still negative 2. That doesn't change. But the negative third power becomes the positive third power. So what you have now is negative 2 at the top being raised to the ninth power over negative 2 being raised to the third power. That's one way to do it. Another way to do it is to simply add negative 3 and 9 at the beginning. Okay, so I'm going to do it my way, and then I'll go back and show it the other way. We're dividing the same base. Negative 2, notice, is the exact same as negative 2. So you could take negative 2 to the 9 minus 3 gives you negative 2 to the 6th power. Okay. So negative 2 to the 6th power, that's an even amount when 2 is raised to the 6th power. We know 2 to the 5th power was 32. 2 to the 6th power is going to be 64. And since it was an even amount, it's going to be a positive 64. That's one way to do it. If you did it the other way and you said, well, wait, it's the same basis, why would I go through all of that work? You're right. Negative 2 to the third power times, it's still the exact same base, negative 2. Now you do negative 2 to the negative 3 plus 9 since they multiply, and you still get negative 2 to the same 6th power that we got at that step. So two different ways to do it to come up with the number 64. Get to it. Example number 2 is simplifying algebraic expressions. Here's one of those examples where it's two different numbers. X to the negative third to the fourth over y to the squared to the fourth. Okay, we're going to, and I said to the fourth for both of them because that's what we're going to wind up doing. This is one of those instances that you'll appreciate the fact that it's variables more than it is numbers, because you don't have to do the last part of the simplifying part like we did on this one right here, where you got to come up with these great big numbers and stuff like that. This one you simply need to multiply x to the negative third to the fourth because it's a power being raised to a power. What that gives you is x to the negative 12, because a negative times a positive is a negative, over y to the 2 times 4 is y to the 8th. So x to the negative 12 over y to the 8th. Now, something is being raised to a negative exponent right here. X is. So all that means, it doesn't mean it's going to become negative. All it means is that it's going to ride the elevator down. It goes down, there's nothing left at the top, so you consider it 1 at the top, because if you put 0 at the top, it'll just be 0. So it's 1 over x to the positive 12th now, since it went down. Y doesn't move. It's still to the 8th. So 1 over x to the 12th, y to the 8th. That's all you need to do with that one, because you don't know what either x or y is equal to. Do this one. Take about 30 seconds. Make sure you raise both of them to the third power. All right, they're both being raised to the third power. So this one gets raised to the third, so it's a squared to the third over this one gets raised to the third, b to the negative third to the third. So just multiply. It's powers being raised to powers. So you multiply 2 times 3 and you get a to the 6th over, again, powers times powers, negative 3 times 3 is b to the negative ninth. We almost finished. If that didn't have a negative right there, we'd be done. You can't leave a negative exponent, though, ever. The only time it's acceptable is when you're doing scientific notation, and again, we're not fooling with that right now. So if you ever see a negative exponent, know that there's one more thing you got to do. This is being raised to a negative exponent. It has to go up. So a to the 6 does not move. It's still at the top of the fraction. B to the negative ninth goes up, and it becomes b to the positive ninth. There's nothing left at the bottom. It's over 1. There's no reason to write anything over 1. So your simplified version of this is a to the 6th, b to the ninth. Or a to the 6th times b to the ninth. Then example B says negative 3, a to the 3rd, a to the ninth, a to the negative 7th. Okay, so they got a lot of stuff going on right there. What you need to make sure you do is negative 3 to the 3rd. This is the product of a power property. It says you could separate them, and all you're doing with this is being raised to the 3rd, and this is being raised to the 3rd. That's all they're showing with this line here. So negative 3 to the 3rd is going to be negative 27, because negative 3 times negative 3 is positive 9, times one more negative 3 is going to back to negative 27. Then all of these are a. You have a times a times a. They're all the same. So you can add the exponents. Remember, when you're adding numbers, don't think of it as plus, because this is adding and this is adding. And the reason I say that is because you're adding a negative number, but instead of writing plus a negative, you could simply write it as minus. Just combine the numbers. 3 plus 9 is 12. 12 minus 7 is going to be a to the 5th power. So negative 27, a to the 5th power. And again, the reason we were able to do that is because all of the bases a were exactly the same. A times a times a. We add the exponents 3, 9, and negative 7. Try this one. Take about 30 seconds or so. Okay, about the most confusing part of this one is that negative in front, that first y. Look at all, if you had to write them all out, they would look like this. Negative 1y squared to the 5th times 1y squared times 1y to the negative 12. So if you had coefficients for all of them, the first one would be negative 1 since it has a negative. The second one would be 1, and the third one would be 1. We're going to put all of those together, and we're going to wind up with either an even or an odd amount that's going to determine if it's going to be negative or positive. First things first, though, we have to make sure we have an exponent being raised to an exponent. So this has to distribute to both the negative 1 and the 2. So what it winds up being is negative 1 to the 5th, and it acts like this now, y to the 2 times 5, which we know is going to become y to the 10th. So negative 1 to the 5th, that's an odd amount, which is going to give us back to a negative 1. Because odds is going to be negative. So then it says times 1y squared times 1y to the negative 12. Okay. So all of your bases are the same. All of these y's are being raised to the exponents. Notice the coefficients in front of them are not being raised. So y to the 10th times y squared times y to the negative 12 becomes y to the 10 plus 2 minus 12. 10 plus 2 is 12, and 12 minus 12 gives us y to the 0 power. We know anything to the 0 power is simply 1, So what that's going to become is 1. Oh, I didn't mean to grab that one. 1. And then when you multiply -1 times 1, it's -1. Times 1 more is going to be -1. So -1 times 1, ultimately the answer to this problem when you simplify it is -1. And then C says c to the fourth d squared over c to the ninth d squared. Make sure both terms get squared since it's raising powers to powers. Notice in the box it says c to the fourth, then it says squared, d squared. You know c to the fourth times 2 is going to be c to the eighth d squared over c to the ninth d squared. So you have the same bases, c and c, dividing by each other. So what that gives you is c to the 8 minus 9. And you have the same bases d and d dividing by each other. That gives you d squared minus 2. Remember, division goes with subtraction, multiplication goes with addition. So c to the 8 minus 9 becomes c to the -1, and d to the 2 minus 2 becomes d to the 0 power. So remember, everything's over 1. But anytime something's raised to a 0 power, it's just like saying times 1. So notice on the next line, it just gets rid of it, and you have simply c to the -1 power. Remember, everything is over 1. Anytime something's being raised to a negative exponent, it rides the elevator down. 1 stays on top, c goes down, and it becomes positive, c to the first power, which is simply 1 over c, or 1 divided by c. Try this one. Okay, first thing you want to do is make sure you distribute that third power in the denominator. R becomes to the third power, s to the -1 gets raised to the third power. So what you have now is rs squared over r to the third, s to the -1 times 3 is to the -3rd. So now we still have same basis, r and r dividing by each other. The first r doesn't have an exponent on it, so you treat it as if it says 1. What that means is r to the 1 minus 2 since they're dividing. Do the same thing with the s's. They're both s. You have s to the 2 minus, and then look what it's subtracting by. It's subtracting by a -3. Remember, anytime you minus a -3, it's the same thing as adding a positive. So 2 plus 3 becomes s to the 5th, and you have r to the 1 minus 2, which is r to the -1. So now you have two variables. One's being raised to a positive exponent 5. The other one's being raised to a negative exponent -1. Everything's over 1. Elevator rule says negative exponents got to go down. S to the 5th over r to the first power, or simply r. And again, since we don't know what either one of those variables is, that's as far as we can go. Then you had two quick checkpoint problems. Being raised to the third power, that gives you 2 to the -3 times 2 is 2 to the -6 times 2 to the 5th. Again, you could say that it rides the elevator, or you could say they're both the same base. 2 to the negative 6 plus 5 gives you 2 to the negative 1. Remember, nothing could stay with a negative exponent. Ride the elevator down. 2 to the negative 1 goes down. 1 stays on top. 2 to the positive 1 goes at the bottom, which is simply 1/2. Everything gets on the top gets raised to the second power. J gets raised to the second power, and k squared does. That means k to the 2 times 2, like this, which gives us k to the fourth, over everything gets raised to the third power at the bottom. J to the negative 1 times 3, k to the third power. So right there, when we simplify all this, we get j squared k to the fourth over j to the negative third k to the third. And again, you have the same bases, j and j. J to the 2 minus a negative 3, which means plus a positive because it says divide by. K to the 4 minus 3 gives you k to the first power. And this one minus a negative gives you j to the fifth power. So j to the fifth power, k, because there's no reason to write it to the first power.